Good morning everyone, and welcome to today's worked exam answer video. Today I am having a look at a multiple choice question which is covering Maxwell-Boltzmann distribution curves, which comes up in the kinetics topic of the AQA specification. So this is a year 12 topic that I am assuming that lots of you who are in year 12 have either covered very recently or are due to cover in the near future. I've chosen a multiple choice question based on this because a lot of the questions on Maxwell-Boltzmann distribution curves that come up in the final A-level papers, for those of you in year 13 watching this, lots of them will be in the form of multiple choice questions because they have other topic areas that they want to cover in the main body of the paper. Also, multiple choice questions, although they may seem a little bit easier, a lot of the multiple choice questions are quite challenging because they've put purposefully kind of close to being correct wrong answers as the alternative options. And in this question, they've given us 4 statements that we have to kind of read through and decide which is correct. So we can't answer this question without reading all the statements, and it can be really easy once you're reading them to kind of think, oh, that could be correct, but that could also be correct, because the people writing these questions are purposefully trying to trip us up, which I know is not very nice, but at least if we know that, we can deal with it as best we can. So in this question, we're told that we have been given the Maxwell-Boltzmann distribution for a sample of a gas, which they've labelled X, at 2 different temperatures. That's why there's 2 different curves on this particular distribution. On any Maxwell-Boltzmann distribution curve, the x-axis will always be energy, and the y-axis will always be either number of molecules in the sample of the gas or potentially number of particles in the sample of the gas. Either way, it's the same idea in that it's showing us how many molecules or particles have different energies within this sample. Now, they've also labelled P, Q, R and S on here, which doesn't actually link to any of the statements, but P, Q, R and S represent the most probable and mean energies for both of the temperatures. And I'll come back to that in a second. Also on the x-axis, we have an arbitrary assignment of the activation energy. So that would be the minimum energy that the particles would need to have for successful collisions to occur. Then it says which statement is correct for the higher temperature. Now, before I even read any of those options, the first thing that I think I would be doing, and I might suggest that you guys would be to do, is deduce which of those 2 curves represents the sample of the gas at the higher temperature. Now, we need to be aware of how changing the temperature changes the shape of the Maxwell-Boltzmann distribution curve. It's the only variable that does, because it's the only variable that we can change that changes the amount of energy that the particles have. If we increase the temperature, we give the particles more energy. If we were to decrease the temperature, the particles would have less energy. So using that knowledge, we can hopefully see that it is this curve here, so the one that peaks at a lower point on the y-axis and that's kind of shifted to the right, that would be for the higher temperature, because all of sort of these particles or molecules down this end have gained more energy, so the peak moves further away from the y-axis because all of the particles or all of the molecules have more energy. Another way to work it out, which I think is really nice, is to use the activation energy mark that they've put on here. So if I was to just draw a line up from the x-axis where they've labelled activation energy up through both of the curves, what we can then hopefully see is that the area underneath this kind of bottom curve is actually incredibly small, and that's going to represent the number of particles or the number of molecules that have energy greater than or equal to the activation energy. Those are the only ones that are going to collide, and when they collide, the reaction will occur. They will be our only successful collisions. However, if we then consider the area under the top curve, we can see that we now have all of these additional particles, or all of these additional molecules, which also have energy that is greater than or equal to the activation energy. And one of the things that we should know for higher temperatures is, because we're giving the particles more energy at those higher temperatures, more particles will have energy that is greater than or equal to the activation energy, and that's why we get more frequent successful collisions, or more successful collisions per second, per minute, per unit time. So if you're not sure which curve is for the higher temperature, we can always look at where the activation energy is to the right hand side of that and see, okay, which curve has more molecules in this case, or particles that have kind of energy greater than that, and then we can figure out which curve is which. So from there, what I'm going to do, just to hopefully make it a little more visual, is I'm going to, very badly as it turns out, go over the curve for the lower temperature and then do the same for the curve at the higher temperature. Again, if we come back to what P, Q, R and S are, which aren't directly mentioned in the 4 options, we can then also see the effects of a higher temperature. So P is the most probable energy of the molecules at the lower temperature. So it's the peak of the curve, so that's where the number of molecules is at its highest. So the most molecules in the sample have that particular energy. The peak of the curve at higher temperature is represented by R, and we can see that the most probable energy of the sample at the higher temperature, the energy is much higher. So that's another way that we can see that the curve that I've gone over in red is at the higher temperature, because the most probable energy has changed. So I'm just going to write that here. P and R represent the most probable, which, if we're thinking kind of back to GCSE maths, that would be like your mode, your most frequent energy. Q and S then represent the mean energy, and the mean energy, like any mean, that's adding up all of the energies that all of the molecules have in the sample, dividing it by the number of molecules to work out what the mean energy would be. And we always find the mean energy slightly to the right of the most probable energy. And again, the mean energy at the higher temperature is a greater energy value than it is for the sample at a lower temperature. So again, we can use those letters to show that this curve, the red one, is the higher temperature. Now, finally, coming on to our options, we have to deduce which statement is correct first of all. Sometimes they will say not correct. They don't say which statement is wrong or false. They go with not correct, again, because some people will not see the not and just see the correct. So, as always, for every question, make sure you're reading it really carefully. So it says, the area under the curve to the left of the activation energy decreases. The total area under the curve increases. The activation energy decreases, or more molecules have the mean energy. So there's a lot of those that sound like they could be correct, or in different scenarios will be correct, but won't necessarily be correct here. So, for example, the total area under the curve, that represents the total number of molecules, or total number of particles. When we change the temperature, we are not changing how many molecules are in the sample. Whereas if we were thinking about changing pressure, it might be that we change the pressure by adding more molecules into the sample. So in that instance, the total area under the curve would change. But for temperature, we're changing the energy that the molecules have, but we're not changing how many molecules there are. So definitely not going to be B. The area under the curve should be the same. And when we draw curves for different temperatures, we have to be as careful as we possibly can be that the area under the curve that we lose here is kind of equivalent in size to the area under the curve that we gain on that side. So that's something that we need to be aware of if you were asked to draw curves like this. C, another one that sounds like it might be correct. It's not correct here, but it would be correct if we were looking at a Maxwell-Boltzmann distribution with and without a catalyst. Adding a catalyst would decrease the activation energy, move this arbitrary point to the left, and then we would have, again, more particles or more molecules with energy greater than or equal to the activation energy. Changing temperature, the activation energy itself doesn't change, but we do get more particles or more molecules that have the activation energy. So again, that is not correct, but it would be correct if we were thinking about adding a catalyst. And I'm going to add the increasing pressure for that one. We would see the activation energy decrease if we were to add a catalyst. D, again, based on what we've talked about already in this video about the mean energy, some students would say more molecules have the mean energy and read that not as it's actually written, but see mean energy and think, oh yeah, the mean energy has increased because the mean energy at the lower temperature was Q, mean energy at the higher temperature was S, the energy of S higher than the energy of Q. But it's not asking us about the energy values, it's asking us how many molecules have the mean energy. And molecules is on the y-axis. So at the lower temperature, we would need to draw a cross from Q like that. That would be for the lower temperature. For the higher temperature, we'd be drawing a cross from S. Trying to draw these horizontally from a dodgy angle, apologies. So we can see that the number of molecules that have the mean energy at the lower temperature is higher than the number of molecules that have the mean energy for the higher temperature. So more molecules have the mean energy at the higher temperature. Not true. It would be less molecules or fewer molecules would have the mean energy at a higher temperature, Now that means that A has got to be correct if we've ruled out all the other options, and A is the correct answer here. If you read A as the first option in the list and you think A is correct, this is where sort of there's tactics and things to consider with multiple choice questions as well, because if you read option A and you were certain it was correct, it may be better to go with it. It depends on how confident you feel, I suppose, because if you think that A is correct, you then don't have to read all of the other options and you don't have to be potentially kind of confused or swayed by the other options. However, if you think it's A but you're not sure, then you may want to read the others, and you might not always be starting with A. Some people, when they do multiple choice questions, they alternate between reading from top to bottom and reading from bottom to top. Obviously, again, that's individual preference. So A says that the area under the curve to the left of the activation energy decreases. Now, when I drew the lines to represent the number of particles or molecules here that have energy greater than or equal to the activation energy, for the higher temperature, we said that the area to the right of the curve would increase. If the area under the curve can't change when we're thinking about temperature, because we're not changing the total number of molecules in the sample, the energy to the right of the, if the area under the curve to the right of the activation energy has increased, it has to decrease on the left, because we have to have overall the same area under the curve that we did underneath the curve for the lower temperature. So if one side of the activation energy's area is increasing, the area under the curve to the left has to decrease to keep the total area the same. Again, if we think about it from what increasing the temperature does, if we're giving the particles more energy, then there will be more that have the higher energies. So the number of molecules on this side, again, we would expect to be lower. So obviously I did the wrong answers first on purpose to be able to show you why they were wrong. But like I say, if you were to see that, identify the higher temperature, read option A and think that it's right, obviously only you would be able to decide how confident you were, whether you were going to not even read the other options and move on, whether you were going to read them just to be certain that you were correct. These are all things that you will figure out with more practice of multiple choice questions and more practice of doing them in exam scenarios as well. But hopefully everything I've said there makes sense. But of course, as always, if it doesn't, please do leave a comment on the video, or if you've got longer questions or other questions you want to ask me, you can always drop me an email to missgtutoringandresources@outlook.com. Thanks so much for watching, guys. Hope you have a fab day.